My projectile problem is a cannon is fired with a velocity of 250 meters per second at 60 degrees. What is the maximum height the projectile can reach? We'll start with filling out our chart and what we can figure out based off of this problem, which is really only the acceleration right now. We know that horizontal acceleration is 0 meters per second squared, and vertical acceleration is negative 9.8 meters per second squared, which is gravitational acceleration, which is what will be affecting this projectile right now. Because we only know that, we'll set up a triangle to help us solve for our other velocities. We can fill out this diagonal side with our 250 meters per second. And right here, we know is our 60 degrees. We can label this side X and this side Y and use SOHCAHTOA to solve for them to find our other velocities. So we'll start with our vertical, which is X. And we can see here that this is opposite and that's hypotenuse, which means sine. So we have sine of 60 equals X over 250. We're going to multiply by 250 on each side to cancel out that 250 and get X alone. And then we get X equals 216.51 meters squared. Meters per second, not meters squared. You can figure that out by putting it into the calculator. Then we'll solve for Y. And here we can see that this is adjacent to the angle. Adjacent over hypotenuse means cosine. So we have cosine of 60 equals Y over 250. Once again, multiply by 250 on each side because you want to isolate that Y. And by putting it into the calculator, you get Y equals 125 meters per second. Now we can transfer that to our chart. For horizontal velocity, initial and final are the same, and that's our Y. So you have 125 meters per second for both parts. And for vertical velocity, initial is positive and final is negative. So here you have a positive 216.51 meters per second, and here you have a negative 216.51 meters per second. I'm going to clear this part off, and we'll do our next step. Now that we have, for our vertical side, initial and final velocity and the acceleration, we can solve for time, which will be the same for both sides. Our time equation is going to be rearranging the acceleration equation. So this is the original acceleration equation. Acceleration equals final velocity minus initial velocity over time. We're going to rearrange it to make this side equal to time. So we'll multiply by time on each side to get AT equals VF minus VF. And we'll divide by A to get T alone. And we'll get T equals VF minus BI over A. So that's going to be our new equation. Now we can start substituting in these values for this. I'm going to clear it off so that we have some more room. And I'll write this equation over here. So once again, our new equation is time equals final velocity minus initial velocity over acceleration. We can fill that in with our final velocity, which is negative 216.51 meters per second minus positive 216.51 meters per second for our acceleration, which is negative 9.8 meters per second squared. Before I do unit analysis, I'm going to simplify this down by subtracting these two, and it becomes negative 433.02 meters per second over negative 9.8 meters per second squared. Now we can put it into unit analysis. So we'll have negative 433.02 meters per second divided by negative 9.8 meters per second squared. One of the s's cancel, both m's cancel, And when you divide those, you get 44.19 seconds, which we can now put in our chart. 44.19 seconds, 44.19 seconds. Now that we have the time, and we're only missing displacement, we can solve the displacement for both sides. Our displacement equation is displacement equals initial velocity times time plus half acceleration time squared. And now that we have these, we can start substituting values in. So if we're doing the vertical side, we get our initial velocity, which is 216.51 meters per second, times our time, which is 44.19 seconds, plus half our acceleration, which is negative 9.8 meters per second squared, times our time squared, which is 44.19 seconds squared. If we put that into unit analysis, it'll be written out like this: 216.51 meters per second times the time plus half times the acceleration. And so that it's easier, we'll write time twice to show that it's squared. Here we have these seconds cancel. We have all the seconds cancel here. And our final answer for that side is negative 0.927, which we can make 0 meters instead to make it easier for this problem. So we have 0 meters for that side. And we can repeat the same thing for the horizontal, just substitute in the values from that side. So, but because here we see that acceleration is 0, anything times 0 cancels out, so this side's not needed. We really just need the initial velocity and the time. So we have it as 125 meters per second times the time, which is still 44.19 seconds. Put it into unit analysis so that we can cancel out our units. The seconds cancel, and our final answer is 5,523.75 meters, which we can also put in our chart. So, now that we have all this information, I like to draw pictures sometimes to help me figure out what we'll need to solve for the maximum height. So if we were to draw our picture, we could draw our cannon. Like this. And you'll see the projectile motion of the cannonball being shot. We already know that our initial velocity on this side is 250 meters per second at 60 degrees. Now, based off of some of our other information, we can kind of figure out what we need. Well, we know that this time is the total time for the problem. So T equals 44.19 seconds. And since this is the top here, and it's in the middle of that projectile motion, we can assume that this time divided by 2 is what the time is here. So if you are to put that into the calculator, you put in 44.19 divided by 2, you get about 22.1 seconds. So we have our times here. If we're finding the maximum height of the problem, we can see that the maximum height is right here. So we don't necessarily need this side in order to be able to solve our problem. So we can cut this down the middle and just focus on this half. Because we're just focusing on this half, we need to change this initial velocity into terms more like this rather than this written at the degrees so that we can solve for it. So to do that, we are going to multiply these two together. So you're going to have 250 meters per second times the sine of 60 degrees. Because if we remember our triangle, when we solved this earlier, to get the vertical velocity, the initial velocity, we use sine. And when you do that out on the calculator, you can write it in unit analysis. 250 meters per second times the sine of 60 degrees. Your final answer is 216.51 meters per second, which we know is correct because it's the same as in our chart. So rather than having it written out like that, we can change this part to 216.51 meters per second, which is going to be easier for us when we're filling out the rest of our problem. Another thing that we know is the vertical component of the velocity at the top of this is equal to 0, because this is a point where the upward motion is stopped and the projectile begins to fall back to Earth. So we know that our velocity up here at this top, v equals 0 meters per second, which is perfect because since we're only doing half, we can call this our initial velocity and this our final velocity. And due to the fact that this is a projectile, our acceleration is negative 9.8 meters per second squared, because once this ball leaves the cannon, it's just the force of gravity acting on it. So now that we have all of this information together, and we have our half time, we can solve for this displacement, which will give us the highest position that this cannonball will reach. So to do that, we're going to once again use our displacement equation, which is x equals, or displacement equals, the initial velocity times time plus half acceleration times squared. And we're going to substitute in the values that we have again. So we have our initial velocity, which is 216.51 meters per second, times our half time, which we're going to use because we only want this part of the problem. If we wanted to find the displacement down here, we'd use the full time, but we don't really need that right now. So we're just going to use our half time. So times 22.1 seconds plus half the acceleration, which we know once again is negative 9.8 meters per second squared, plus that time again, which is a half time, 22.1 seconds squared. We can put that into unit analysis so it's easier for us to cancel everything out. So we have 216.51 meters per second times 22.1 seconds plus half negative 9.8 meters per second squared. And once again, we'll write the time twice, 22.1 seconds, 22.1 seconds. Our seconds cancel here. Our seconds cancel here. And after putting this all out into the calculator, our final answer equals 2,391.63 meters. And that is your final answer for the maximum height the projectile can reach.